we start the second part of the lecture, which was for singularity. In this part, I will deal with singularity and its relation with Laurent series of a function, which that series has the domain of convergence annulus. So we start with a function f z equal to. So we start our journey with a function f z equal to e to the power 1 upon z, which we are familiar with, and we have already seen that z equal to 0 is essential singularity, isolated singularity of this function. But here we are interested in the series expansion of e to the power 1 upon z, which seems to be very natural to be written in this form. And see, e to the power 1 upon z is analytic everywhere, except at the point z equal to 0, where it is not defined. So it makes sense of this series, which I have written here, which is written in an annulus whose inner radius is 0 and outer radius is infinity. So it's actually punctured complex plane, punctured at the point 0. And but see, something very interesting happens here. This series is here, powers of z are negative, or you can say they are a non-positive powers are there. The first term, the power of z is 0. Otherwise, all powers are negative. So it is not a power series, first of all. Second, all the terms except the first one, they have z, the exponents of z is a negative. So what type of series this is, in which category it comes? So you have already seen, I think you must have seen in this refresher course, somebody must have given the series expansion of analytic function around a point, Taylor series or power series. And here comes the Lorentz theorem, which deal with such type of series, which are called double series, or series which contains positive as well as negative exponents. So suppose this f is analytic function, or holomorphic, whatever you want to say. So here analytic is saying, better thing is saying analytic, because we are talking in terms of series. In an annulus, this annulus has, this is the annulus, this annulus A, we can, this, in fact, this annulus can be drawn here. So this is suppose annulus, and this is your point. This is your point z naught. So this is one radius. This is r1, and this may be another radius r2. So your annulus part is this is your annulus. So the annulus is this one, and your function is analytic inside the annulus. So this function is analytic inside the annulus, and then function f can be written as a double series. One part is of a negative exponent, and other part is of non-negative exponent. And this part, sometimes they say this part is called principal part of the Laurent series, which contains only a negative exponent, and it is a very deciding factor about it will decide the nature of nature of singularity of this point z naught. If we take the disk punctured at z naught, of course. Here I have written a very general type of figure I have made, but when we will deal with isolated singularity, then the disk will be there, punctured at a point that will be annulus of inner radius 0. So anyway, so this Laurent theorem says something about this one. So here I have taken only the circle. Actually I have taken, this is not necessary to take. You can take any simple closed curve, because any simple closed curve is analogous to this circle, which is of radius small r. So this is your gamma. This is positively oriented, you are saying. It is simple, not crossing itself. It is closed and enclosing the point z naught. Then all the coefficients of can be written in terms of this integral, and this is a Laurent series centered at z naught. So now here comes the classification in terms of Laurent series. So if now now suppose z equal to z naught is an isolated singularity of function fz, which is analytic or holomorphic in some punctured disk d of certain, some punctured disk means of certain radius, disk d punctured at the point z naught of radius r. So I'm talking about a disk which is punctured at z naught. So this disk is nothing but an annulus actually. So it is collection of those points where z minus z naught mod is less than is less than. There I have made certain mistake. It's just okay, right? So z minus z naught is less than r and greater than 0. So inner radius is 0 and outer radius is r, and this is your disk. So now I write the end and Laurent series is given by of this function in this disk is given by of this function is represented by this Laurent series in this annulus, it's a punctured annulus, where k equal to -1 to infinity ck. So now the principal part will be the deciding part. So concentrate on this part for classification. So the classification will be this one. Z naught is a removable singularity if fz if if a star, the Laurent series, if a star has no terms of negative exponent, means it becomes simply, it means fz is represented by, uh, fz is represented by a power series around z naught, represented by a power series. So the singularity is called removable. Second is pole. So z naught is pole of order m. Z naught is pole of order m if the principal part of Laurent series, star is the Laurent series. The principal part of the Laurent series terminate terminate at some some negative exponent. That is, your series take this type of term. Your series becomes, it is something like this: k is equal to -1 to m ck z minus z naught plus positive part. This is part from k equal to 0 to infinity. And here c, sorry, here c minus m is not equal to 0. C minus m is not equal to 0. And every other term, and it can be seen easily that c minus k is 0 for all k greater than equal to m. Oh, sorry, all k greater than m. All k greater than m. And it may happen that some k's which are less than m, for that, for example, c minus 5, m is c minus m is non-zero. It may happen that c minus m minus 1 may be 0. Some lower term may be 0. So uh, some other terms, some other coefficient here may be 0. But after m, nothing is visible. Nothing will be there. So this is called pole of order n. And if c minus 1 is non-zero, and every other coefficient is 0, c minus 2, c minus 3, c minus 4, then it is obviously called simple pole. So pole of order 1 is called simple pole. And third is classification. It's a very useful classification if you want to do the calculation. And third classification is z naught is an essential singularity. Z naught is an essential singularity if infinite number of CKs, infinite number of CKs where k is less than 0. Infinite ck is r non-zero. Means the negative coefficient are c minus 1, c minus 2, c minus 3, c minus 4, up to c minus infinity, up to infinity, minus infinity. So up to minus infinity. So infinite number of them will be non-zero, as is the case with x. See, it is example is here. E to the power 1 upon z, you can see here. E to the power 1 upon z. It has infinite number of coefficients are non-zero. See, c minus 1 is 1, c minus 2 is 2, 1 upon 2, c minus 3 is 1 upon 6, and so on. In fact, all the non-zero, all the negative exponents are sitting there with a non-zero coefficient. So therefore, e to the power 1 upon z was essential singularity. So this is a very nice classification and beautiful classification in terms of a Laurent series. So now I just want to give one example. I just want to demonstrate that whatever we have done in part 1 can be seen here also in terms of the series also. For example, consider consider function fz equal to sine z upon z. Sine z can be written as it has a series expansion, and its series expansion, I think you remember its series expansion is z minus z cube plus its series expansion is z minus z cube plus z5 and so on. And you can see very clearly that it is 1 minus minus no negative exponent, no negative exponent. so by our this first rule, it is sine z upon z. By first rule, z equal to 0 is a removable singularity of sine z upon z. So here I have written this, but I have done this thing here. I have done it here. I have written it specifically here. Now see, I take this point. I take the point. Here I take the point. See here, this function fz has two isolated singularity. One is at 1 and one is at -1. So if you see carefully, so here one singularity is sitting here at 1 and one singularity is sitting here. One singularity is sitting here at -1. And both singularities are, we have easily seen both singularities are both these singularities are pole, and actually these singularities are simple pole, and that can be seen here. I give you one calculation here. Suppose I take this one I take this singularity. Around it I expand the function. So 1 upon z minus 1. So this can be written as z minus 1 plus 2. So takes the form 1 upon z minus 1 minus 1 upon 2, and it becomes 1 upon 1 minus z minus 1 upon 2. And it has a minus 1 upon 2 z minus 1, and it has a power series. It is a series expansion. 1 upon 1 minus z, and mod z, it 1 upon 1 minus z when mod z is less than 1 can be expanded as 1 plus z square plus z cube and so on. So it can be written as 1 plus z minus plus z minus 1 and so on. And this becomes minus 1 upon 2 z minus 1 plus, oh, this is again minus, this is minus 1 upon 4 minus, this one will be how much? Z minus 1 upon 8 and so on. So anyway, see here, only c minus 1, which is minus 1 upon 2, is non-zero. And everything c minus m is 0, where m is greater than 1. C minus 2 is 0, C minus 3 is 0, and everything is 0. And it means z equal to 1. It means z equal to 1 is a pole of order 1, means simple pole. So I have written here one application, but this is not exactly the application of singularity, but it is something you can consider for calculating the residue, and it's a very strong idea because you are computing some integral only knowing the negative, the coefficient of a negative exponent of in the principal part of Laurent series. So if this is a Laurent series, it is given here, a Laurent series given here. And if you consider all these, if you consider this Laurent series is given in this annulus, and if you z equal to z naught is isolated singularity, so I make it 0 here. So it is better that I put it 0 here. So, and just simply I put R. Why to take this trouble of putting it this thing? So this is simply R. So an annulus is there. Then you have written the power series Laurent series expansion, and gamma is a positively oriented curve, as we have seen here. This is a punctured, it is actually a punctured disk we are taking, and this punctured disk we have taken. This is punctured at z equal to z naught. This series is punctured at z equal to z naught. Then what we do, we write if we take, here I do, if we take any simple, close, positively oriented contour. Contour means the piecewise smooth path around that point, z naught. Then you can compute the integral of the function, and which is nothing but the coefficient of 1 upon z in the Laurent series expansion multiplied by 2 pi I. That's a very powerful result actually. And this c minus 1, which is used to define, to give, or to compute an integral, is called a residue of the function at z equal to z naught. And the residue is a very strong concept used in computing integral. In fact, the real integral, a real improper integral, is being computed with the help of residue. So here I give one more result, which is more of the nature. It is not connected with a Laurent series, but it gives the residue, uh, is given at residue. We give the residue at a singular point, which is pole of order m. So here I give. So this is a, so because we are talking about computing the residue, which will help us to compute some integral. So it is it will be nice if I give you one theorem which gives something about a residue when isolated singularity is a pole. So if z equal to z naught is a simple pole of function f, and of course I have considered that I am taking everything is taken care, because it is a local property of an analytic function we have studied around a singular point. So we are talking everything, we are talking in terms of a disk or a neighborhood uh, around the point z. So if it is a simple pole, then you can actually, there is a formula for computing residue of this function at this simple pole, and that residue comes out very simple. It residue comes out phi z naught if pole is simple. What is this phi z naught? So actually we know this phi z is coming. If z naught is pole of order m, then fz can always be written in terms of this phi z, z minus z naught to the power m, where phi z naught is not zero. Phi z naught is not zero, and phi z is analytic at z naught. So it's an analytic function in a neighborhood of point z naught. Fz is not analytic at z naught. You know, z naught is pole of fz. Phi z is analytic at z naught, and every fz is a function with pole at isolated singularity z naught, then it can always be expressed in this form, in a unique way. So this pole is called of order m. So phi z naught is nothing but the value of, because phi z naught is not zero actually. So phi z naught is a non-zero. It is non-zero complex number at z naught. So it is phi z naught is residue if m is equal to 1, and if z naught is a pole of order m, then where m is greater than 1, for example, then what I mean by residue. So here you have to do a little bit of here you have to compute the derivative of that function phi z, which is analytic. And you know, if phi z is analytic at z naught, so it's all order of derivative axis. So you have not to check all. If so, you have to check the derivative of order m minus 1 at point z naught, and this is m minus 1 factorial. If m is, I have written m is greater than 1, yes, m is greater than 1. So this gives again you the residue. So it's a very nice idea to get the residue. For example, you remember what was our function of pole? So, for example, consider the function fz equal to sine z upon z square, which we have done in part 1. You remember z is this z, you know, this z was simple, 0 was a simple pole, 0, a simple pole. If you remember, we did the calculation in first part. So z equal to 0 is a simple pole, and if you want to find out residue of fz at z equal to 0, so simply what you have to do, you have to So residue of z equal to 0 is nothing but here the function itself. You see nicely this function fz is written in this form, but simple pole at. So here I will write it how to write it. So if it is simple pole, means I have to find a function whose value will be at phi 0. So what residue it will be? That's a very interesting point. What will be that thing? So what do you mean by phi 0? The value of function is non-zero at z naught because it is analytic. It is analytic at z naught means uh, its limit is some non-zero number there. So here, see, this is function. So don't get disturbed upon z. Therefore, z was sin z upon z. This phi z is nothing but so at z equal to 0, its value is not 0, its value is 1. So am I correct? So it is 1. Am I correct? So we check it. Sin z upon z square. Sin z is what? Z minus z cube upon 3 plus z5 upon 5 upon z square. This is 1 upon z minus z upon factorial 3 and so on. So actually, see, when I say the value at 0, the phi is analytic function at 0. Sin z upon z is analytic at z equal to 0 because, its singularity is removable actually. So it's a perfectly analytic function and its limiting value will be phi z naught. So actually, phi 0 is nothing but z goes to 0 sin z upon z. That is one. So here we stop self. Here we are stopping ourselves. And I have given you some, again, for this part, there will be some multiple choice questions which you have to do. Wish you all the best. Hope you got something out of these two lectures.